Hello students. Today we'll try to understand concept of electrostatic potential. We'll see definition of electrostatic potential. We'll see the basic expression for electrostatic potential, and we'll also try to understand the difference between absolute potential of a charge at given point and relative potential. Okay? So let us start. Before we start today's topic, we need to know certain things from previous lectures. First of all, we should be knowing that in uniform electric field, when we move charge, the work done can be given as W is equal to QED cos theta. What is theta here? Theta is angle between the force QE and displacement D. So when force and displacement are perpendicular to each other, work done is zero. We are not spending any energy. When the two are in same direction, work done is positive. When the two are opposite, work done is negative. Then if we have non-uniform electric field and sorry, there if we are moving any charge, then work done can be given as integration of electric field over displacement from infinity to p with q outside, and this is how we can find out work done to bring charge q from infinity to given point p, which is in electric field of source charge. And then of course we know that electric field is conservative field, and that means that whichever path you follow, work done remains same. It depends only on initial and final position of charge. So if you have any doubt in any of these points, you should go back to previous lectures and check those videos and then come to this topic. So I assume you have these things clear, so let us start. Consider a charge q1, and let there be some point p near the charge, and we know that this q1 is having its electric field in its vicinity. Even though there is no other charge, q1 is having its electric field. It's only that we realize about the electric field when we bring some other charge close to it. Now consider another charge q1, which is at very large distance, maybe infinity, and from there when we bring the charge to point p, uh, we need to do work. Why do we need to do work? Because electric field of q1 is in this direction away from q1, and our test charge, if we call it test charge, it is brought against the electric field. So we are spending our energy, and so this work done W1 will be positive. And where the energy is going, the energy spent to bring Q from infinity to point P is stored in the system in form of potential energy. We'll discuss that at greater length in forthcoming videos. For now, if we focus on work done, we are doing work, or work is done on this charge q, not by the charge. Work is done on charge q. Okay, now consider another charge q2, and let there be similar point p again at same distance, and again we consider our small charge small q, and let us bring it again to point p, and now the work done is w2. Now what is this e? This is electric field of q1, and what is this e prime? It is electric field of q2. Okay, and as the electric fields are not same, w1 is not equal to w2. Okay, let us define a quantity now. Say w1 by q and w2 by q. Now if you look at this quantity, and suppose if we calculate and we uh, come to the result where w1 by q is less than w2 by q, what does it mean? What does it mean? This means that q2 Q2 is greater than Q1, isn't it? Because Q2 must have higher electric field, and so it could make it more difficult for us to bring small q from infinity to point P. This quantity is a quantity which is giving us influence of charge, maybe it is Q1 or Q2 at given point, because more the charge, more the work done. And so it is very similar to electric field, with only difference that here we are talking about work, here we are talking about energy, and it is scalar quantity. But understand that this W by Q quantity is independent of which charge you are bringing. It may be 1 coulomb charge, it may be 10 coulomb charge, which is brought from infinity, makes no difference, because ultimately you are dividing the work done with the charge being brought. Okay, so W by Q is a quantity which is independent of charge which is brought, but it depends on the charge uh, who is providing field, who is having its influence in its surrounding, source charge we may call it, and hence this quantity W by Q is a quantity which is giving influence of a charge at given point in its surrounding. It is scalar quantity unlike electric field, but similar in some manners. This quantity is called electrostatic potential. So what is electrostatic potential? W by Q, work done per unit charge. Which work? Work done to bring a charge from infinity to given point against the field. Obviously we are working against the field, because if you are coming against the field, then you are doing work. Okay, what if it is negative charge? Suppose Q is negative charge, then electric field is towards the charge, displacement is also towards the charge, and in that case work done will be negative. Work done on the charge will be negative. Work done by the charge is obviously positive. And this quantity is called electrostatic potential. So let us check the formal definition of electrostatic potential. Electrostatic potential is defined as the work done to move unit positive charge from infinity to given point in the electric field against the field. Now the question here is, why infinity? Why we need to bring charge from infinity? Okay, before we address that question, let us see electrostatic potential of point charge once again for slightly different condition. Consider a Cartesian coordinate system with axis x, y, z as shown here, and let there be O as origin. And at origin, we place our source charge q, and let there be point P at a position vector r. And we consider our test charge at infinity at very large distance. And how do we find out work done to bring the test charge q from infinity to given point P? We want to bring it here. So in this case, this is the direction of electric field, and so when we are bringing q, obviously there will be repulsion, and our task will be difficult. We will have to spend energy, but then our energy spent is stored in the system in form of potential energy. So in this case, uh, if we go back to definition of electrostatic potential, it is work done per unit charge. So work done is infinity to point P, force dot displacement. What is QE? QE is force dot displacement. So it is scalar quantity. Q and Q gets cancelled out. Now look at the direction of electric field. It is away from capital Q. Look at the direction of displacement. It is towards capital Q, and hence what is the angle between the two? Obviously 180. And then we get one negative sign here. This negative sign is indicating that work done is against the electric field. Okay, and that is how we define electrostatic potential. Now the question remains, why infinity? Why can't we bring it from some point, say x to point p? Why we have to bring unit positive charge from infinity to point p? Okay, consider that we have an object placed on some table, and you displace it and keep it at some height h. Now, can I say my work done is force dot displacement, so it is mgh here. Now, does it mean that mgh is the potential energy of this object? No, mgh is not potential energy of this object at height h. It is difference of potential energy, actually negative. So whatever was the potential energy of the object earlier, it is changed by mgh. It may be increased by mgh or it may be decreased by mgh, but you cannot say that mgh is the potential energy of the object at this height. The proper sentence is the change in potential energy of the object is mgh. Okay, and if I want to say that mgh is the energy of the object, then I need to make sure that earlier the energy of the object was 0, and obviously earlier the object was in influence of gravitational field, so its potential energy was not 0. Very similarly here, when we are at infinity, when the charge is at infinity, we understand that influence of capital Q on small q will be 0, because at infinity this source charge would not have an electric field, so initial potential energy is 0. And then when we come to point P, we can say that we have done work, and work done is change in potential energy, but as initial potential energy is 0, if I am doing 50 joule work, the potential energy of Q is 50 joule. Okay, so why to go to infinity? Because at infinity we may assume that initial potential energy is 0, but it is not necessary that you go to infinity. And what if we are not coming from infinity, rather we come from some other point in electric field? So what will be the difference conceptually and in terms of expression? Let us see. So let us consider again Cartesian coordinate system xyz. Let the origin be O, where we place our point charge q, and now there is a point A at position vector Ra, and let there be one more point B at position vector Rb. So if I come from infinity to point A with my test charge small q, I'll need to do some work, and that work done per unit charge is potential of this point, sorry, potential of this charge at this point, isn't it? And if I come with my test charge at point B, I can say that it is potential of q at point B. And if you are coming from infinity, it is said to be absolute potential. Absolute means whatever work you do is energy. It is not difference of energy, is energy, because at infinity initial energy is considered to be 0. So we know that work done to bring unit positive charge from infinity to a point can be given as this. Let it be VA. There is unit positive charge, so we have +1 coulomb here. Okay, and why negative sign? Because we are doing work against the electric field. Similarly, if you bring unit positive charge from infinity to B point, how do we express potential in that case? So from infinity to B point, when we come, the electrostatic potential can be given as minus infinity to B E dot dr. Though dot doesn't make any sense here, because it is simple multiplication of two numbers E and dr. Direction part is considered in the sign. Electric field and displacement both are opposite. Now, as I said, what is this VA? It is work done. What is VB? It is work done And as we are bringing the unit positive charge from infinity, it is considered to be absolute potential at point A, absolute potential at point B due to source charge capital Q. But what if I go from B point to A point? Suppose I have small q here and I go from B point to A point. What will happen then? So right now, assume that my work done to bring unit positive charge from infinity to A point is say 50 joule. Suppose work done to bring unit positive charge from infinity to point B is say 60 joule. Then what will happen if I go from B point to A point? Obviously the work done will be less, because from infinity when you come to A point and from B when you come to A point, uh, infinity to A and B to A, obviously B to A work will be less than the previous one. This is called potential of A with respect to B point. This is called potential of A with respect to infinity, and infinity means initial potential is 0. So this potential is considered to be absolute potential, whereas the later one is considered to be relative potential. But both are potential of the same point A due to same charge capital Q. But in one case we are making sure that initially unit positive charge is not possessing any energy, whereas in second case initial energy may not be 0. So now when we bring unit positive charge from infinity to point B, it is infinity to A integration. But if the charge, unit positive charge, is brought from B point to A point, then this is how we can find out potential. What is V prime A? Potential at this point due to this charge. But as you are bringing from B, unit positive charge is brought from B to A, it is called potential of A, potential of point A with respect to B point, and hence this is called relative potential. So mathematically you can simplify it further. Instead of writing integration B to A, we can say first I will go from B to infinity and then I will come from infinity to A. So B to infinity and then infinity to A. So why to do so? Because we have expression for this journey, infinity to A, we know it is absolute potential of A. Infinity to B, we know it is absolute potential of B. So V prime A can be written as this. What is the change made here? Just this. Instead of infinity to A, the integration, this second term is brought here, and instead of B to infinity integration, we have mentioned infinity to B. So this negative sign will become positive. Now here we know that infinity to A is VA and infinity to B integration is VB. So V prime A can be written as VA minus VB. This is called potential of A point with respect to B, and this is called relative potential of point A with respect to B. What is VA? Potential of A point. What is V prime A? Potential of A point. What is the difference? In this case, work is done to bring charge from infinity, so it is called absolute potential of A point. And what is this? Potential of A with respect to B, so it is called relative potential. So that is the only difference between absolute and relative potential. So let us conclude now. So electrostatic potential is defined as work done to bring unit positive charge from infinity to given point in electric field against the field, and it can be given as minus integration of electric field over displacement from infinity to A. Again, negative sign indicates that work is done against the electric field, and as it is infinity, if you are bringing unit positive charge from infinity, it is absolute potential. And potential of charge q at a point with respect to some other point, which is relative potential, can be given as integration from b to a, and it is relative potential. And as it is work done per unit charge, one obvious unit is joule per coulomb. Work upon charge is joule per coulomb, but conventionally potential is expressed in terms of volt. Okay, so that was all about the potential and its concept. We'll discuss the electrostatic potential for various charge distribution and different system at greater length in the coming videos. Thank you.